You're putting energy into the magnetic field, taking it out, putting it in, taking it out. It does no work. You're just storing energy there, bringing it back. The work is done on the end of the wire where you got a resistor or something. Okay, that is this. Now, the phase angle, if you measure the amps across that circuit, it's going to be higher than what it would be at the load. So those amps times the volts gives you the volt amps, right? And then this is the kW. Now the power factor is the cosine of this angle right here. Trust me, just say, okay, I believe you. I believe you. Just believe me and memorize this. And I've had a lot of computer folks that we've spent a lot of time on this, and they finally get the hang of it. But most of the computers you get have about a 95% power factor. So this line right here is basically out like this, and then you K-bar. So you have very little bars. This is the magnetic field part of it, right? Is this? I'm getting some stares. Is this? Okay. I'm going to give you a problem.
Only the EEs can try.
I'll give you a problem later on, and then we'll figure it out. But I'm trying to figure out how to explain this. This is real work, and this is what you size the chillers by, because that is the heat you've got to take out of the room. This is how much current's flowing through the transformer, because you have more current flowing in the transformer, because not only are you supplying current to the load, which is resistive, you're supplying current to that magnetic field that's going in and out. So this amp is higher than this amp down here. Same voltage, right? So if you have a low power factor, high power factor, which means a low angle here, you just about have a resistive load. Your great big computers, Titan for instance, has like a 0.99 power factor. So this angle right here is just very, very slight. I don't even make a difference between kVA and kW. But a lot of servers and things like that, they'll get 95, 93% power factor. And you got to be careful, because if you don't, you may overload your electrical equipment, because it's looking at volt amps rather than kW. So now this is interesting here. If I have a rotor and a protractor, I can do all my electrical calculations, right? Because it's all vectors and angles and stuff. So here's a delta, and here's a Y inside the delta, and the neutral is exactly in the midpoint. This is 120 degrees. So let's say I've got a voltage from phase to neutral that's equal to 1. If I do my trig, 60 degrees, this is 0.87, 0.87. So the voltage phase to phase is the sum of that is 1.73, which is square root of 3. If you do your trig identities, that's what you'll find out. It's very simple. I mean, it's no big secret. I just spilled the beans. Y'all know now all about electrical engineering. I'm sorry. So when you got three-phase voltage or single-phase voltage, three-phase voltage is, delta voltage is big, phase-to-phase voltage is a higher number, phase to neutral is a lower number, and the difference is a 1.73 multiplier. Okay, here's your problems. I'm going to do all right.
Okay.
Based on the information thus far, which of the electrical distribution configurations would be best suited to meet RFP requirements, and why? Now, go read this. This doesn't have anything to do with electrical engineering or anything like that. But it's a very good article on just doing stuff. Basically, try something. Because if you don't try nothing, you haven't made a mistake. You can't be correct, you can't learn, you can't do nothing. Give it a try. Pick one of them and justify why you're doing it. I don't care if you're right or wrong, but do something. Try it. And this one here is calculate the currents for the diagram below. I got a 12470 primary transformer, a 480 volt, 277 volt secondary transformer, and I've got a load that's 83. That's kVA instead of RVA. It's a balanced three-phase load. Look on the internet and see if you can find something. I mean, try it. Just try it.
So this is in the Blackboard and on the Google Drive, so you can get the problem out of his presentation.
I was going to talk about the floor plan. Now here's the fun. I'll let y'all read this. Google has they've announced they're going to build a data center in Stevenson, Alabama. 100 kW. It's going to be on sustainable energy eventually. There's no TVA coal-fired plant there that's being shut down. Okay. Let's assume that you're planning this. You're the systems engineer trying to figure out what you got to do. And you know that you can't get it out of wind energy, because I used to live on the mountain above that and they don't have a lot of wind. So they got to do solar power, right? This is Google's announcement. This is a solar farm in California, it's 500 kW. This is Raccoon Mountain, TVA's Raccoon Mountain, their pump storage. Figure out how many square feet or square miles of solar panels you have to have for this, and figure out how many Raccoon Mountains you have to store off-peak energy. Now that's the kind of stuff you do. I mean, literally, that's the kind of stuff you end up doing sometimes, trying to figure this stuff out. And then if you figure out, hey, we can do it, then you go back and you get into the minutia of all the details and everything. But you got to look at it from 10,000 feet. Say, can we do this? This is fascinating right here. They got a simulated picture from space. You can see their solar farm from space. It's so big. But it gives you an idea of how hard it is to get those kind of power levels from solar farms. So, if you got time, don't have nothing else to do. So, any questions? 2 minutes, 3 minutes over.
All right.
Any questions? No questions?
Yeah. All right. Thanks, Rick.
No. All right.
All right.
Good deal.
All right. Have a good weekend.
See you.
I'll see you.